first use case we're going to dig into is product virtual prototyping. And by extension, we'll sort of show a lot of the fundamental functionality of the SDK and how to set up a single simulation and work with the results and post-process the results and so on. So let's imagine that you are a headset manufacturer and you want to optimize the headset you are designing or producing, either the hardware itself, the form factor, the positions of the microphones in the microphone array, things like that, and you want to be able to virtually prototype that in a variety of acoustic conditions. Or you're developing some kind of algorithm that's within the device, potentially a data-driven DSP algorithm, and you want to generate high-fidelity data to train or evaluate that algorithm. That's exactly what the SDK is made to do, and we'll show this right here and now. So in this kind of scenario, you would like to set up a virtual audio scene. And an audio scene can look something like this. So it's a simplified sketch where we have the receiver device in question with some microphones on it. Then we have some environment with some furniture and stuff around and things like that. We have some, let's say, call it target sources or speech sources and things like that you want the device to pick up. And you have some distractor sources like the coffee machine or whatever that you want to reduce. And we can set up the audio scenes very easily in the SDK, have them simulated with high precision, and render device-specific output for those scenarios. I'll show it here for kind of setting up one scenario, but it's also very easy to do it at scale to set up 10,000 scenarios. We'll look at that a bit later today. So I'm just going to walk through the code here. The first block is just about kind of, let's say, logging in to the SDK and creating a project, which we call here DRTF, Device Related Transfer Function Example. And there are a few ways to get the geometry in question. You can use the geometry database, you can programmatically generate rooms. We'll look at both of those in a bit, but also you can import room geometries. That's what we do here. We support a wide variety of 3D file formats, such as 3DM, SKP, DXF, OBJ, and so on. So pretty much all CAD tools can output in at least one of these formats. And it's simply this code here to import and add the model to the Treble SDK. I've already run that, so here I'm just going to display the model in question that I'm going to work with. It's a model of an apartment. We are going to set up an audio scene in this sort of kitchen living room space within the apartment. You can see that the 3D model, the surfaces, the walls and so on have been grouped into layers, which will facilitate material assignment, which is indeed the next step. So the Treble SDK comes with a huge database of all kinds of acoustic materials that you can use in your simulations. These materials are grouped into different categories, and right now I'm just fetching different categories from the database and pulling them into these variables here. And then I create a little function which randomly maps a material from a given category to a layer in the 3D model. And I do that for all the layers here. And now this function is ready. And then the way I assign materials in this particular case, you can go about it in different ways, but what we do here is that we say, please kind of iteratively assign random materials according to this function to the different surfaces until the Sabine estimated reverb time is in this range of 0.3 to 0.4 seconds. And it takes a few iterations until it's hit some group of materials on the different layers. If I would run this again, then I would get different materials, of course. And the Sabine estimated reverb time is within this range. Okay, we have a room, we've assigned materials. Next step, sound sources. The SDK comes with a very big database of all kinds of sound sources that you can use in your simulations or in your audio scene generation, which we see here. And the first thing I'm going to do is I'm going to pick two sources from this database. On the one hand, a speech source, and on the other hand, a particular Genelec speaker, the 8020. And I'm going to plot the directivity of the speech source just for fun. At low frequencies, it's quite omnidirectional. At high frequencies, it's directional, as expected. All right, we can also import directivity into the SDK, either if you have directivity in the CLF, common loudspeaker format, or if you just have raw data, a balloon, a directivity balloon. It could be in an Excel sheet or in a CSV file or whatever, where you basically have frequencies, points on the sphere, and then the complex frequency data or the balloon data here. And that's what we do here. We've kind of created a little helper function here to fetch the measured balloon, and then we basically have these arrays of data, and we add that to our source library. Okay, so now I've kind of chosen what sources I'm going to work with. Now I'm just going to put them into the audio scene. So I make a list of sources here. First, I put the speech source in a particular location and give it a particular orientation as well. I also add an omni source somewhere in the room. I add the Genelec 8020 somewhere. And finally, this custom source with the raw balloon data, I also put that in there as well, and I give these sources some labels and so on. That was the source part. Then for the receiver, I'm going to put 3 receivers into the space, and I'm going to have them be spatial receivers, meaning that the output is an ambisonic room impulse response, and then we can work with that further in post-processing. So that's really kind of the fundamental steps of doing the simulation. Room geometry, materials, sources, and receivers. And now let's see how we run the simulation, obviously, but also how we then work with the results to get the device-specific output. And we have this very cool functionality for rendering the device-specific output. So we need to run the room simulation and get out these very high-fidelity, high ambisonic order spatial room impulse responses, but we only need to do that once, and then we can in post-processing render the device-specific output. We can change out the device, we can rotate the device, all in post-processing very rapidly. And this way you can augment data and so on very quickly. And the way to get the device data into the SDK to then mix with the spatial room impulse responses, there are 3 ways. If you have a measured HRTF or DRTF, then you can import that in a SOFA file. You can also import a device CAD, and Treble will simulate that for you, and you get the DRTF just directly from the CAD. I'll demo this in a second. Or if your organization has a library of some kind of receiver devices, that is, then you can also use that. Okay, so here first I show how to import, which would be this path here. From a SOFA file, it's really just a few lines of code to import this into the SDK. We've already run that block, so we've imported this KeyMar mannequin. It's from a database from online, but we also added 2 other devices as well. On the one hand, sort of a mannequin with a headset on it, and the headset has 2 microphones on each ear, 1, 2, and then here as well, 3, 4. And then something of a fictional smart speaker, which has 3 microphones on the top here. And then we are going to run the room simulation and then work with these devices in the post-processing. And I fetch these devices here. This guy here we call DJ Hats, the smart speaker, and the KeyMar mannequin as well. For running the room simulation, I can set some settings. For example, I say that the ambisonic order of the spatial receiver should be order 32. It's a very high order. The Treble offers this capability of working with these very high order ambisonic impulse responses, which is needed if you want to get physically correct results, device-specific spatial results for a broad range of frequencies. We can set some other settings of the solver. You can also just use default settings, but we're just showing an example here. And then we create the simulation definition. We tell it to be a hybrid simulation. So for low mid frequencies, we do a wave-based approach. For the high frequencies, we use geometrical acoustics, switching between the two at 4,000 Hertz. We tell it to simulate long enough until there has been 20 dB of energy decay in the room. We put in these receivers, sources, materials, and settings. And we can plot the setup here of this audio scene that we've now generated. We can see here something of a dinner party, you can say, where we have a couple of sources here, which can be people talking. This is the speech source. This is actually the omni source. And then two sources here, which could be some kind of distractor sources from the TV and from the coffee machine, say. And then we have three receiver positions, these spatial receivers, which we will mix with the devices in post-processing. And we can see all the materials that we assigned and so on. All right. And in order to run this simulation, I would simply run these 3 lines of code here. It takes a few minutes to run the simulation. I've already done it just to save some time. So we can simply, with these lines of code here, fetch the latest simulation results from this project. And then we can start working with the results. And I'm going to show the device-specific output for these different receivers in different receiver positions and different orientations. We use source number 1, which is the omni source here, and we're first going to look at receiver number 1, which is this guy here. And if the orientation is, or rotation is 0, 0, 0, that means the receiver is looking down the x-axis here. And I'm going to render results for DJ Hats, which was the mannequin with the headset. And we see here the impulse response. And if we zoom in on the very early reflections, or the direct sound on the early reflections, we see that microphones 1 and 2 have the same amplitude. These are the microphones on the left side. And then the microphones on the right side have lower amplitude and of course arrive also at a later time. If we then rotate the device and re-render again, we will of course see something different. Now it's microphones 1 and 3, which are the microphones on the front of the left and the right ear, arrive at the same time and with higher amplitude, and the microphones on the back of the device on each ear have lower amplitude. We can then switch out to another device, smart speaker, render that. That has 3 microphones, not 4. Now they're looking straight kind of at the source here, but maybe we can have the same orientation, so looking down here, but go to this receiver here, receiver number 2 instead, but using the smart speaker and re-render. Then we see that the impulse responses, or the direct sound, arrives at different times because it's coming kind of from left to right across the microphones on the device. We can look at the Keymar mannequin as well. Which is just the binaural signal. And then of course the ear facing the source is louder than the ear on the other side, essentially. This might look slightly more noisy than the results before because the Keymar HRTF is a measured HRTF, whereas the smart speaker and the headset was simulated DRTFs. We can look at the frequency response, of course, as well. And yeah. So this is basically a simple example of showing how you can generate device-specific output in complex audio scenes very easily with very high precision, and then use that to virtually prototype hardware or machine learning audio algorithms. And now maybe a natural question would be to ask, how accurate are these simulations? It looks pretty cool, but is it really matching reality? And the next step here is that we're going to show a quick benchmark comparing measurements and simulations for these kinds of scenarios. All right, let's dig into this particular validation case here. It concerns a small or sort of small to medium-sized room of 80 cubic meters in size. It's a room here in Reykjavik, which we have measured in great detail and then used for benchmarking simulations. And we consider the room under different conditions. First of all, being empty, but with varying levels of reverberation by having varying amounts of absorption on the walls. Then we took 10 tons of bricks into the room and kind of laid them around in random positions to really make the geometry of the room very complex. But the reason we chose bricks was to still keep the material properties relatively simple, but very complex geometry. And then finally, we went sort of the whole way, where we both have complex geometry and complex material properties by introducing a lot of sort of traditional furnishing like sofa and chairs and tables and things like that into the room. And we measure both mono and binaural room impulse responses. The binaural impulse responses were measured with a KEMAR mannequin. And it's a bit of a spoiler here, but basically in all cases we see a very good match between measurements and simulations, but let's of course dig into the details. And in this case, we ran a wave-only simulation in all cases. That's very practically doable in a room of this size. Okay, let's first look at the empty room. It looks something like this. We excite the room with a directional sound source, and of course in the simulation we also use a directional sound source. We consider a variety of source and receiver combinations, and in the simulation for the receiver, when it comes to the binaural part, we use this approach that I just showed earlier, where we simulate a spatial room impulse response, and then in post-processing we mix the spatial impulse response and the HRTF to get the binaural or the device-specific output. But if we first look at the mono results, here in the time domain, we see an excellent match between measurements and simulations. The early reflections are captured very nicely and the overall energy decay as well. If we look in the frequency domain, also a great match. The low to mid frequency modal behavior is captured nicely and the high frequency trend is also captured very well. Energy decay at different frequencies looks very spot on. It of course helps that in this case we know the material properties of the wall materials quite well. So there's good input data into the simulation. These are acoustic parameters. This is T20 and this is early decay time. Great match observed. Note, for example, here in the mid frequencies, this interesting increase in reverberation. This is due to a 2D sound field living between two hard parallel surfaces, which is very well captured in a wave-based simulation. And then the binaural results also look fantastic. This is the right and the left ear for one particular source-receiver combo. Clearly the receiver's right ear is facing the source. We can also have a listen. Here we have an anechoic recording of a speech signal and a music signal. And then we've convolved that with the binaural room impulse responses, both the measured ones and the simulated ones. And let's have a listen. First, the anechoic speech sounds something like this.
Noise and poor acoustics have been shown to be a major factor impacting our health, well-being, and productivity.
And then in the measured room.
Noise and poor acoustics have been shown to be a major factor impacting our health, well-being, and productivity.
And the simulated room.
Noise and poor acoustics have been shown to be a major factor impacting our health, well-being, and productivity.
And for the music, first anechoic. And the measured room. And the simulated room. I hope it comes through clearly in the webinar and in stereo and all that, but I can at least say in my totally unbiased opinion that they sound actually very similar. Okay, now we turn to the complex geometry case where with all the bricks, the 10 tons of bricks, it looks something like this. So the geometry of the room has been modified substantially, and it's a much more complex case, you can say. But the results look, I would say, equally good as before. Here we're looking at mono results, time domain excellently capturing these early reflections, room modes again captured very nicely, and the overall high frequency trend as well. Energy decay still looks absolutely spot on. And binaural results with the Kimar mannequin also look fantastic. Look at these early reflections here and the difference between the right and the left ear. Same with the frequency response, the room mode behavior here, and the high frequency trend, the ear canal resonance, and these things are all absolutely captured in the simulation. And finally, the furnished case, where it looks something like this. And yet again, measurements and simulations match up very well. This is one particular source receiver combo. Here's another, looking equally good. Energy decay, very good. And binaural results look excellent as well here in the frequency domain. So this goes to show that the Treble simulation engine is really capable of producing real life-like quality audio data, simulation output, device-specific output, as you would get from real-world measurements. Now let's move to a different thing. I'm going to show a new feature. It's a bit of a, so actually everything we're showing in today's webinar is production-ready features available to our customers. We will also share these notebooks that we're demoing with everyone who's signed up for this webinar, so you can give them a spin yourself if you're either a customer or have a free trial. The only thing which is sort of a coming soon thing is what I'm going to show next, which is the capability of generating a DRTF or an HRTF from a CAD file. Let's take a look at that. And we're going to demo a prototype of it here. So the workflow here is as follows, that the input to this DRTF generation from CAD is that you import the CAD of the device, for example, a smart speaker. You set some settings on this DRTF generation simulation, and then a free field simulation is run where sound is radiated actually from the microphone positions of the device to a sphere of receivers around. So you essentially have a transfer function from all different incidence angles to all the different microphones. The results of this simulation are then essentially converted to the spherical harmonics domain and stored as a DRTF. You can then store it in the library of devices your user or your organization has. And then, of course, you can use this just as I did before in simulations, in post-processing, in rendering, and so on. So let's take a look at this part here in this prototype. First part, as usual, is just sort of to initialize and log in and so on. Once that's up, then I'm uploading a CAD model, in this particular case within a 3DM file, of a fictional smart speaker that we've made here, which looks something like this, where the speaker is here and the microphones are here. I then set up this free field simulation, setting some settings such as the frequency range I'm interested in, the number of points on the sphere. There is some relation between how many points you have and what ambisonics order you use. This can be seen in our documentation. And then I specify the location of the different microphones on the device, essentially. And that's really all that's needed to set up and run the DRTF generation simulation. Then I can simply run it here, or if I've already run it, which I've done in this case, then I can fetch the results from some IDs and plot and explore and so on. So this is the setup of the DRTF simulation. So the domain is a sphere here. The device is in the center, and then there is all these receivers around. And if I zoom in here, we can see the microphone positions here, and then we simulate essentially the free field response from all these microphones to all these receivers on the sphere. And that's then what makes up the DRTF dataset. Once it's the simulation is run, we simply run this create DRTF command, and that's already been run, and we can add it to our library of devices. And that's it. Then you have your DRTF good to go, ready to augment data, create 100,000 room responses with this device in 10,000 different audio scenes or whatever you would like to do.